Moving on to the next talk. This will be by Yuting Wang, and this is on fully composable and adequate verified compilation with direct refinements between open modules.
What happened? Hello, can you hear me? Okay, I'm going to talk about verified compilation of open modules with direct refinement. It's a joint work with those people. So the state-of-the-art of verified compilation is, of course, CompCert, which has many great applications. The idea is that if you have a C program, you compile it with CompCert, you generate a sampling program, you can derive a refinement between the source and target semantics. This refinement is represented as a simulation between small step executions. In the original CompCert, you can only support whole program semantics, which means you must enter from the main program and return from it. When we move to the open modules, then the entry point may be something other than the main functions. For example, in this figure, we enter from F, and you may also invoke external calls. So in this talk, I'm going to use the black arrows to represent the internal executions, and the blue ones to represent the external executions. And in this case, at the different language levels, the program states, you will have a specific language states. For example, at C level, you have function calls. At the target level, you have register states. And also, the memory state is exposed. So you need some kind of, this refinement will need some kind of invariant to relate those states. And we want this refinement to directly relate the source C and the target assembling states without having the user to know how the compiler is implemented. But this is not the case for the existing work. In the compositional CompCert, you have a single refinement which uses C interface, which basically means the assembling semantic is distorted. It needs to interact through the C function calls. And in CompCert M, the refinement is a union of refinement which is derived from the compiler passes. And in CompCert O is a concatenation of refinements. So basically, if the user wants to use this kind of refinement, to a certain extent, he has to know how the compiler is actually implemented. So what is the difficulty? The main difficulty is the compiler has like several passes. If you approve the refinement for the individual passes, how can you actually vertically compose them in an open module setting? So basically, how can you hide those intermediate semantics? So we provide the answer to these questions by developing an approach to direct refinement that supports all the important features for compiling open modules, including vertical and horizontal composition and the equivalence between the semantic and syntactic linking, meaning there's no distortion of the semantics. This is also known as the adequacy property. We also support the heterogeneous modules with free calls between them. And this approach is applied to the full compilation chain of CompCert starting from C-Lite. So we believe this first version supports the direct refinement. And there's also extension to user level verification, meaning you can have a direct refinement from a high-level user specification all the way to the assembling programs. And in this work, we basically focus on first-order languages with global memory and pointers. So let's take a look at a running example. And this example consists of two modules, a client and a server. So the client will accept requests for encryptions, and you will forward those requests to the server. So a typical interaction is environment initiate the request. For example, it wants to encrypt the value 11. And then the client calls the server, calls the encrypt function by passing this value. It also passes a callback function called RCD to the server. And the server performs encryption by XORing the value with a secret key, which is 42. And it stores on the stack frame of the server at the address RSP plus 8. And then it passes this pointer back to the client. And then client will read from this pointer, read this result, and store it in a global variable. So why this program is interesting? Because it actually have non-trivial like ping-pongs between two different modules, and also passing of pointers between the client and the servers. So you have like a leak of pointers, memories. And so intuitively, this should be verified in 3 steps. First is that you prove the CompCert is correct. Then from this direct refinement, it guarantees the refinement for the client. For the handwritten server, we need to design a specification and also show this specification refines the implementation through the same direct refinement. And then by vertical and horizontal composition, we can propagate this refinement all the way to the link to the target program. So I'm going to talk about this in reverse order. I'm going to first talk about the second and third step, and finally the first step, because the first step is the most difficult one. So first, let's take a look at what this direct refinement is and how it guarantees the adequacy and horizontal computation. So the direct refinement between thin and assembly is basically a forward simulation with 2 ingredients. One is the invariant between the source and target program states. For example, the source C program, C function calls, it should be mapped to the register and the memory state according to CompCert's C calling convention. There's also a single injection from the source memory to the target memory. The second is protection of the program states across the external calls, which basically means that if you perform external calls, the external call cannot modify the private state of the system, so that when the external call returns, the simulations can resume. And the adequacy is trivially guaranteed in this case because, as we just discussed, it just directly reads C and the assembly state, so there's no distortion of the semantics. The semantic linking and syntactic linking is just the same. Second is a horizontal composition of direct refinements. This is guaranteed by the what is called the direct protection of the private states. For example, it requires the callee saved register and the stack pointers is not modified or restored when the external call returns. It also enforces a certain form of memory protection, which we'll discuss very shortly. So this protection enables the classical relay guarantee reasoning, which means the simulation relies on the environment to provide a certain guarantee, and then in turn it will provide the guarantee to the caller. And if you have a symmetrical relay and the guarantee conditions, then you can do the horizontal composition because they will cancel each other out. This is the case for the direct refinement in our setting. Okay. So those are some basic concepts, but the difficult part is how do you do the vertical composition of those direct refinements? And this relies on this notion of a transitive Kripke Memory Relation. Recall the challenge is that we have those individual refinements, how we can compose them into a single one. And this is basically, if you zoom in into 2 consecutive refinements, it basically means you need to compose the relay guarantee conditions into a single relay guarantee condition. How this can be done, let's first take a look at how this memory protection is performed. Basically, the memory protection is realized by this INGP relation. What it says is that at the external call, you take a snapshot of the caller's memory. And from this snapshot, you infer which are the private memory you want to protect. Then in the callee, you cannot modify those private memories. The private memory has 2 parts. They are those shaded areas. The first is the source memory that is not in the domain of the injection, which means it is dropped by the injection. And the second is the one that is out of reach from the target, from the injection in the target memory, which means it's not in the image of the injection. Let's take a look at the example. This is a snapshot of the memory with the same execution sequence we see before, just before the server calls back to the client through the RCD. And you have those shaded areas which are protected, which basically contains, for example, return address RA and the pointer that links back to the previous stack frame. And during the call to the client cannot modify those private memories. For example, you cannot secretly modify your return address. So when the client returns, it can safely resume the simulation. So how do we do the vertical composition? So in this case, we have these INGP relations. And the observation is that the INGP is actually, in its protection, it works for all the compiler passes. So you can basically replace all the relay guarantee conditions with INGP conceptually. And also, it's actually intransitive. So it means 2 parallel INGP it can be composed into a single INGP. Okay. So in this way, you realize the hiding. The proof of a transitivity is actually quite non-trivial. The key step is at the external core point, and you want to pretend that you only have a single INGP relation. But so we start from a composition of two injections, and these injections get evolved throughout the external core. When we return from the external core, we want to go back to our actual implementation, which is this parallel refinements. So what we need to do is we need to split this evolved injection into two and construct an interpretive memory state. And this state must satisfy this INGP relation. So the problem is how we construct this. And previously, this problem was thought as very technical and difficult without relying on some kind of extensive changes to the verification framework. But what we find out, this is also the main technical contribution, is that this is actually an inherent property of INGP. So the idea is that the protection you get after you compose two refinements is stronger than the individual protection. So let's take a look at this example. So you have first injection represented by the solid red arrows, and the blue, and the second injection by these blue arrows. The top left blocks, it's actually not protected by the first injection because it's in the domain of the first injection. But it is protected after the composition because its target block is dropped by the second injection. And similarly, for the bottom left memory block, it is not protected by the second injection, but it is out of reach from the first injection. So after composition, this is protected. In the end, most of the memories are protected. The only one that is public and can be modified are the memories that is injected through from the source to the target by those two injections. So to construct this M2 prime, the idea is very simple. You basically copy all the protected memories over, and then you project the updated public memory from the source. And this respects the parallel INGP because we have just said the protection after the composition is actually stronger than all the individual compositions. So this is the key idea and the observations we made in this paper. By adopting this idea, we build a CompCert with the direct refinement. The left table shows the relay guarantee condition for the individual compiler passes. And the condition is basically has a form with an invariant indexed by some protection. So if the protection is the INGP, then you compose two of the conditions. Those two INGPs will be merged into a single one. We also have a weaker protections for passes that doesn't need such strong protections. But in the end, everything will be absorbed into this INGP relation. And this is a naive concatenation of all the relay guarantee conditions of all CompCert passes. And by using the rewriting rules, we can finally rewrite it into this direct refinement. So the CA INGP basically says there's a direct connection between C and assembling through this INGP relation. The RO is optimization. It enables optimization such as constant propagations. And then you also have well-timed conditions, this WT relation. The last one is just always hold for the assembling program, so it's not significant. Okay, so this is the work we have done. We basically developed a version of CompCert with the direct refinement. So we actually show that the direct refinement for realistic verified compilers are possible. The key discovery is that the Kripke relation with memory protection is actually intransitive and applies for all the compiler passes. And I think this kind of relations is actually quite general and can be applied to other compiler verification projects. So all the artifacts are online, and you can check it out. And there's also like ongoing future works by reducing this, connecting this direct refinement back to the whole program correctness of a CompCert, and also connect with the user-level program verification. And we are also experimenting with applying it to other first-order languages like Rust. Okay. That's it, and thanks for this.
Thank you. Thank you very much. Questions?
Hi, it's lovely to see this actually being done properly, but I always thought the problem was that logical relations don't compose, and here you're in a first order setting, right? So, I mean, does what you've done have anything to say about what would happen in a higher order language? Because I always thought that was where the real problem lay.
Yeah. That's a very good question. And basically we are working in the first order setting. So, but even in the first order setting, it is not so obvious those things are composable. So what the technique, maybe some kind of theoretical insight is, with strong enough protections, those things just become homomorphisms, the invariants. So their homomorphisms are naturally composable. But when you move to the higher order setting, of course, logical relations are not composable in general. So I'm not sure how much this, but there are also work on the proving transitivity of the special cases of logical relations that have a similar flavor with this construction of interpreting state in this work. So maybe for those special cases, this technique will work. But in general, I think it's a very hard theoretical problem, and I don't know the right answer.
Thanks.
Thank you. More questions? Okay.
Hi. So this transitivity argument that you showed, it seems to involve some kind of separation argument between states. So would this suggests that maybe this might work nicely in a separation logic rather than a regular logic? So
so in this case, I think we didn't actually employ any a separation logic reasoning, but there are compiler passes in CompCert that has built-in reasoning that based on separation logic. So I think in that case, the proof of those passes already taken care of those properties. So we just reuse the proof as it is. So basically in this technique reuse the most of the CompCert proofs. The real problem is writing at the boundary of a modules how you do those transitive compositions.
okay. So you don't think there would be anything to gain here from using some kind of separation logic for this argument?
I think if you want to extend it into other compiler passes, even in the whole program setting, you need some kind of separation logic. But the proof seems to just work in this open setting as well. So that's my guess.
Okay, thank you.
Okay. More questions?
Maybe this is the same question again, and maybe you said this and I missed it, but could you spell out the assumption on the footprint of the assembly versus the C that you have here?
Oh, this one?
Well, in general, what are you assuming about the assembly?
So I get what it is. So basically, we follow. So this work is based on the CompCert. The approach is that even if you are writing an assembling program, you have to give it some kind of specification in terms of label transition systems using the C interface. So this refinement between the server and the specification must interact at the C level. But internally, we don't care what this implementation is, but it has to act according to the C calling convention. Yeah. So that's why this compositions works. And I know that many people are interested in linking with arbitrary assembling programs. But in our case, if you don't get a kind of a C-level specifications, then the linking, you just cannot link. But I think this is also the difference between our work and the previous work. The previous work always try to do those two things together, like linking with arbitrary assembling program and proving the compiler correctness correct.
But you can, for example, pass in the address of some complicated C structure, and the assembly can walk that structure.
Yeah, if it is not protected by the C.
Thank you.
Yeah.
All right, thank you. Let's thank Yuting again.